Okay, this section is about trig derivatives, and we're going to prove a few things, and you need to know how to prove these um, theorems, and I'm going to show you. So just for a reminder about the trig functions, when you have a number inside a sign, you can't bring it out in front. That doesn't make sense. And it could be any number inside that sign. It's not brought out in front of the trig function. And this is true. This is for any trig function. Sine, cosine, tangent, cotangent, any of them. So the first thing we know is that sine x is continuous. There's no breaks or gaps in the graph. So the limit as x approaches sine x, you can use the substitution property, and sine of 0 is 0. So that's the first one. Cosine is continuous also. So limit of cosine x as x goes to 0 is cosine of 0, but that's 1. Okay, so those are simple things to see. Here's a graph of sine, and it makes sense that as you're approaching 0, your graph is going to 0, so right there. And for cosine, same thing. Here's cosine. This is sine x, cosine x. As you're getting closer to 0 on the x-axis, your graph for the y values are getting closer to 1. So again, that should really make sense. Okay, now I'm going to prove this. We're going to say the limit as t goes to 0, sine t over t is equal to 1. And we're going to use a unit circle to prove it. So here's the proof. And we're going to stay in the first quadrant. We're going to say theta is between pi over 2 and 0. And here's theta. So this is 1, and this whole thing is 1, because the radius is 1, the unit circle. Draw this down, and let's say this is A, and this point is B on the circle. We'll say this is D, and we'll come up here and make another triangle, and this is C. So let's first talk about the area of triangle or origin OAB. Okay, that's this. That's a right triangle. And let's let this be y, and the sine of theta is opposite over hypotenuse, so y is equal to sine theta. Now remember, the area of a triangle is 1/2 the base times the height, and here well, we're going to do, let's do triangle O. Okay, so we'll do all the triangle. We'll do 1/2 the base is OA, and the height is sine theta. Okay, we can also say area of triangle ODB, okay, that's this one, is 1/2 base times the height. The base is 1 in this case, and the height is y, which is sine theta. And then we have the area of the sector. A sector is like a piece of pie, and that's this shape, where this is theta. And that's 1/2 r squared theta. That's the formula for area of a sector. And our r, since it's the unit circle, is 1, so sector ODB area is 1/2 theta, because r is 1. Alright, well, if you look on the picture, we can see that the area of triangle ODB is less than the area of the sector ODB, because the triangle's inside that sector. And so far we have 1/2 sine theta is less than 1/2 theta, so this says sine theta over theta is less than 1. Okay, so that's our first hypothesis. All right, if we look at this triangle OAB, then tangent theta is, we call that y over OA. But y was sine theta, and tangent is sine theta over cosine theta, so that means OA is cosine theta. Okay, so let's see what we have so far. We have the area of triangle ODB is less than the area of the sector ODB, which is less than the area of triangle ODC. And this was 1/2 sine theta. This is 1/2 theta, and this is 1/2 let's see. Okay, I did this. It was also, let's see, C. Let me do this. Tangent theta is also CD over OD. And this is 1. OD is 1 because it's a unit circle. So CD is tangent theta. So going back to this, the base of ODC is 1. And the height is CD, which is tangent theta. So let's go to a new page. What we have is sine theta less than tangent theta. Now if we just look at this, then that says theta is less than sine theta over cosine theta, or cosine theta is less than sine theta over theta. But that was less than 1 that we previously shown. Now, if we take the limit as theta goes to 0, this goes to 1. This is already at 1, so this goes to 1. So by the squeeze theorem, And we can go back on this and say equal to also. If you go back and just change all those lessons to less than or equal, that's an okay thing to do. So by the squeeze theorem, sine theta over theta is squeezed to 1. Okay, so this is an important limit that we're going to see. Next, also we're going to show that one minus cosine theta over theta, or the other way around, cosine theta minus 1 all over theta equals 0. Okay, here's the proof of this. We're going to multiply by the conjugate of the numerator. On the top, we get 1 minus cosine squared, which is sine squared. We're going to break that apart into the limit we just did. And that goes to 1. And this goes to 0 over 1 plus 1, which is 0. So that's 0. Alright, now how do we handle these limits? I'm going to do a few examples. Suppose you want the limit of sine 4x over x as x goes to 0. Now, we're not pulling this 4 out right here. That has to stay inside. That's inside the sign. So what you have to use is the fact that the limit as a goes to 0 of sine a over a is 1. But that means this number inside the sign and this denominator have to be the same. So we're going to make it the same. What we're going to do is make the denominator of 4x by putting a 4 there, but then if we're dividing by 4, we have to multiply by 4, so we didn't change the problem. Let me write that as 4 over 1. So we added this 4, and we added that 4. So now we have this number and this number the same. And that says that that goes to 1, sine a over a. So this is 1 times 4, which is 4. The answer is 4. Okay. So I want to see the work when you do these problems. Now here you have 5x inside the sign. So you have to make the denominator 5x, but there's a 2 there. Well, what we can do is take that 1/2 in front, take this 2 out in front. And again, we have to make the numerator and the denominator the same. So we're going to put a 5 in the denominator to make those the same, but then we have to make the 5 in the numerator to get rid of it, so they cancel out. So right here, since 5x and 5x, sine 5x over 5x, that goes to 1. So this goes to 1/2 times 1 times 5, which is 5/2. Now, we're not canceling anything or doing anything like that, so it's important here how you get to the answer. The steps are very, very important. There's no canceling going on. Okay, here we have to break this apart. We need a 3x in the denominator, so I'm going to put a 3x in the denominator and make those the same, but then I have to multiply by 3x. And then for the denominator, I already have sine 4x. I need a 4x in the numerator, and then I divided it by 4x to get rid of it. So we can show that the limit of a over sine a is also 1. It doesn't matter where the sign is, numerator or denominator. So this is also an important fact you're going to use here. Okay, now that I have these two the same, that goes to 1. And that goes to 0. That goes to 1. Okay, that doesn't go to 0. I can't change that because the x's are going to add out. Okay, so that goes to 1, that goes to 1. 1 times 1 is 1. Then I have a limit, x goes to 0 of 3x over 4x. The x's cancel. And that gives us 3/4. So again, it's important how you work the problem. Limit x goes to 0, 2x plus 1 minus cosine x over 3x. We're going to break this apart. We're going to do 2x over 3x. We're going to do these. And then you should recognize that over x. So that's going to be plus 1/3. I can pull the 3 out in the denominator in the second part. And I have 1 minus cosine x over x. So this is 2/3 plus 1/3. And this limit is that important trig limit, and that goes to 0. So this is 2/3. Okay, one more. Okay, you should be able to see this. I do the x over sine x. I'm breaking it apart. And then I have tangent x over sine x. Well, that goes to 1. This is sine x over cosine x times sine x. You invert multiply. So that's 1 over cosine x. Limit of that as x goes to 0 is 1. So this is 1 plus 1, which is 2. Okay, so why did we do those limits? Well, because that leads us to finding the derivatives of the trig functions. We're going to prove that using the limit definition. Okay, so number 1, we're going to do sine x. We're going to use this definition. We'll go through the proof. That's sine x cosine x plus cosine x sine h. There's h here. Minus sine x over h. So I'm going to take these two and factor out the sine x. You should recognize that. Here's what's left over. Now we saw that goes to 0. That's trig limit. This goes to 1. So that's 0. This is cosine x times 1, so it all goes to cosine x. So that says that the derivative of sine is cosine. And the same way, Cosine's derivative turns out to be minus sine x. So these are two important things. So if we want 2 sine x, the derivative, well 2 is just a constant, so that comes out in front. We just take the derivative of sine, so the answer is 2 cosine x. What if we want the derivative of sine squared x plus cosine squared x? Well, we don't take the derivative of each one. What you should notice is that that's Pythagorean identity. That's just 1, and the derivative of 1 is 0. So be careful because you're going to use trig identities here to do some of the derivatives. All right, look at some of the example homework problems, and that should help you out some more.